Okay, now once we prepared the LR0 items, now we are ready to construct the SLR parsing table. Here what we should just keep in our mind is those items in LR parsing tables, whether it is SLR, whether it is CLR, whether it is LALR. The items are corresponding to the rows of the LR parsing table. So since we have generated 12 items, that means the resultant parsing table, the SLR parsing table, will have 12 rows, 12 rows or 12 status. So we should structure the SLR parsing table as the action part, so all LR parsers parsing table contains two subsections: the action subsection. This generally those item the parsing table is a single parsing table, but internally divided into two sections: the action part and the go-to part. The action part and the go-to part. Action part is used for specifying the possible actions that can be taken by the parser, and the go-to part is used to indicate the change of state. That is the state, how it should change from one state to another state, and the possible actions that can be taken by the parser are the shift action, the reduce action, accept action, the shift action, reduce action, and accept action. So those are the possible actions. And error entries, those empty entries of the parsing table indicate error entries. Those all are error entries. So shift action is abbreviated or symbolized by S, and accept action ACC, and reduce action R, small r. And those numbers are representing the production rule number. So reduce by, this indicators reduce by production number 4, reduce by production number 2. So if once we created those set of status or set of items, we should structure the parsing table as a two-dimensional structure having 12 rows. So each row is corresponding to each state of the LR0 item. So state 0 is representing I0, state 1 representing I1, or row 1 representing state 1 or I1. And here what you have to keep in your mind is the two sections are sharing the rows. The rows are shared by the two sections. So when we are referring, for example, in go to table, when we are referring the first row, we should consider state 0. When we are referring row 0 in action table, we should also refer the same state 0. Now once we structured the parsing table as actions and columns, then their column action and go to sub tables or subsections. Then we should indicate the columns. So in action table, the columns are the terminal symbols. So as you can easily observe from the given grammar, the terminal symbols are id, plus, star, opening bracket, closing bracket, and finally dollar sign. So here this dollar sign is not a terminal symbol in the grammar, but it is used as a terminating a special character. That's why it is added as column in the action table. And in go to table, we just place the non-terminals of the grammar. So we have non-terminals E, T, and F. From the given grammar, we have E, T, and F. So just excluding the non-terminal that we have used for augmenting the grammar. So here, once we just structured, now we are ready to insert or to place the actions and those status. So then first, how we can fill the first row? The first row can be filled by considering the item 0. So item 0, now we consider item 0. So how we can place those actions is by executing the actions of the algorithm construction, parsing table construction algorithm. So here the first step is constructing or creating the item collection. That is, we have already done, because we have created the collection. By applying the closure and go to operations. The next step is filling the action table. And the action tables, in action table we should fill the actions shift, reduce, and accept, and the remaining empty entries will be considered as error entries, and error action will be taken. So how we can fill the shift action? This is very simple. So to fill the shift action, we should check from the given item, if in the item, if after dot there is terminal symbol, we should fill shift action in by taking the item as an argument, as an item, the item which is generated from the item by shifting the position of dot after the terminal symbol. So for example, if we consider this action, how S5 is added under id column is because in item I0 we have id after dot, and item I5 is generated from I0 by shifting the dot operator after id. Look, here we have id after dot, and I5 is generated from I0 by applying the got operation and shifting the position of dot after id. So shift 5, that's why shift 5. So on the row 0 we just fill sorry, S5, and 5 is indicating the state from which we generated the item or the state that we have generated from I0 by shifting dot after id. And how this S4 is filled is we have opening bracket after dot on I0. Look, this one is the one used for adding S4. S4 because here I4 is generated from I0. I4 is generated from I0 by shifting the position of dot after opening bracket. So that's why we added S4. And there is no other action that is added under the other columns. The other columns are left blank, and those are indicating error entries. So why? Because the others are non-terminals after dot. Here after dot we have E, after dot we have T, after dot we have T, after dot we have F. So for those production rules we should fill under goto. So the goto table or the goto subsection is just filled by if there is non-terminal after dot operator. So on the row 0, under the goto table E1, why this one E is filled? Because we have generated state I1 from I0 by shifting the position of dot after non-terminal E. Look, so E I1 after shifting position of dot after E, we generated I1. So here when we are, what you have to keep in your mind is when you are filling the entries of goto table, you should take only the state numbers, not the with other symbols, just simply taking the state number. So I1 we just took only 1. For I2 we just consider only 2. For I3 we consider only I3. So I1 is generated from I0, I2 is generated from I0, I3 is generated from I0 by applying goto pressure operation on I0 comma T, then F, then E. The same is true for row 1. So here we should check I1. So in I1 we have, this is final item and this is final item, but here for final item, according to this algorithm, if the item is final item, so we should fill reduce operation. But if the final item is the one by which we augmented the grammar, then we should fill accept action under that state I1 and under column on the row I1 and under column $sign. That's why we have added accept action under $sign on this row 1. And for I1 this is not a final item, but after dot we have terminal symbol. So since we have a terminal symbol, we should just add shift. So every time we detected a terminal symbol after dot operator, we should add the shift action and the state number that is generated from I1. So as this I6 is generated from I1, we should fill S6. That's why we have added S6 here. And why we added accept action? This accept action is added because this final item is the one we have used for augmenting the grammar. And the I3, that is the state or row 3, we have those actions. So reduce action. Now how this reduce to or R2, R is for reduce and 2 is just the production rule number. So that means R1, R2, R3, R4, R5 and R6. So excluding the production rule by which we augmented the grammar, we can just give a number for each production rule of the grammar. So for minimizing the space requirement of the parsing table, we can just simply use R for reduce and the number to indicate the production rule number. So in R, for example, in this row, R2, how this R2 is filled under plus, we should go to I2. So in I2 here, as you can see, this is a final item. So for this final item, we should fill reduce action. According to this algorithm, as you can see here, if the item is final item, we should calculate the follow of non-terminal A. The follow of non-terminal A. So once we calculated the follow of non-terminal A, we can identify columns, because the result of follow of A will be set of terminal symbols. Set of terminal symbols immediately followed the terminal A from each production rule of the grammar. So here in this state I2, since this one is the final item, we should calculate follow of E from the grammar. So as you can see here, follow of E is plus follow of E. As it is a start symbol, we should also consider $sign as the follow element of follow of E element. And again here closing bracket is also another element in follow of E. So we should add the reduce action, and this production rule number is 1 2 R2. So R2 will be filled under $sign, under closing bracket, and under plus. That's why we have added R2 under plus, R2 under closing bracket, sorry, and under $sign. So similarly, you can just fill the other rows. Now, after we constructed the parsing table, you can just see the parsing table to decide whether the grammar is SLR grammar or not. So as we have discussed in our previous session, that there are only two types of conflicts: shift reduce conflict and reduce conflict. So if any one of either of shift reduce or reduce conflict observed in the parsing table, then we can say the grammar is not SLR parsing table. For example, if we filled R2 and another filling another step of the construction of the parsing table. For example, if we have already filled R2 in the entry, in this entry, and at another step of the construction, we also reached at the condition where we can we should also insert R6 into the same entry. So this is the existence of reduce conflict, because we have two different reduce actions added in this entry. If we have, for example, added S5 for D, and we also adding R4, for example, this is indicating the existence of shift reduce conflict. So if we observed any such condition or conflict, then we can say the grammar is not not SLR grammar due to the existence of the conflict. But here in our example, as you can observe, there is no any entry of the parsing table which is having the conflict, either shift reduce or reduce conflict. And keep in your mind that there is no shift conflict. There is only shift reduce and reduce conflict. So this is very important statement. Every SLR grammar is ambiguous, but every unambiguous, but every unambiguous grammar is not SLR grammar, because some unambiguous grammars may not be SLR grammar. But if a given grammar is just SLR, then we can conclude that the grammar is unambiguous. Let you consider this grammar to check whether this grammar is SLR grammar or not. So you should augment the grammar first, then creating the LR0 items collection, then constructing the parsing table, checking whether there is any conflict in the parsing table, then conclude whether the grammar is SLR grammar or not. So as you can see, we can augment the grammar like this, and now we can generate the items. So as you can see, there are 9 items generated from 10 items, because we have started from 0, I0. So 10 items are generated from the given grammar. And as you can see, even without constructing the parsing table, we can observe the existence of conflict from this item. So for example, in I2, obviously this I2 will be corresponding to the row 2, row labeled 2, or row 3 on the parsing table, SLR parsing table. So this, because of the existence of equal sign after dot, we will fill shift action under column equal sign on in the action table, in the action part. And here, this one is a final item. We will fill the reduce action under all terminal symbols in follow of R. And here follow of R are the equal sign and dollar sign. Follow of R is equal sign and dollar sign, because follow of R is follow of S, and follow of S is dollar sign, as it is starting symbol of the grammar. And the follow of R is also follow of L, and follow of L is equal sign, one is equal sign. So this is how we can calculate the follow of R. So under, as it is equal sign is also observed in follow or an element of the set of follow of R, we should also fill reduce action under equal sign on the same row I2. So this indicates the existence of reduce shift or shift reduce conflict, So this, because of this conflict, this grammar is not SLR grammar. Another example, this simple example you can just consider. So you should augment the grammar first, then generate the items. But even without completing the generation of all possible LR0 items, you can observe the existence of reduce conflict in row 0, because here for example, this follow of A, this will be requiring the addition or the insertion of reduce conflict, reduce action, because this is a final item. So reduce conflict because of this one. So follow of B is AB, and follow of A is also AB, because after A we have A, after B we have also A, after A we have B, after B we have B. So both non-terminals having the same terminal symbols in their follow set. So under the same column A and B will have a reduce conflict, reduce conflict. So there are two reduce conflicts in the same row and column. So because of this grammar is also not ASLR grammar. So the next one is constructing scalar parsing table. So this in scalar parsing table, this is very simple concept. In scalar parsing table, here we just reduce the unnecessary reductions, or we minimize unnecessary reductions. So here how we can just avoid unnecessary reductions is by adding parameters. As you can remember, when we are adding reduce action in the case of SLR, we just calculate the follow of the element or the non-terminal after that is appeared on the left hand side of the final item, and add the reduce action under all terminal symbols existed in the follow of the non-terminal. But that is not the case in CLR. What we should make is we create or we add parameters. The terminal symbols are added as parameters when we are generating LR1 items. And here, as we have discussed, in constructing SLR, I mean CLR parsing table, we create LR1 items, not LR0 items. So here, what is LR1 item is, we can just mathematically simply express LR1 item as LR0 plus parameter. So LR1 is used for constructing CLR parsing table as well as LR parsing table, but SLR is using LR0 items collection, and the others two, CLR and LR are using LR1 items. So what are LR1 items and how we can represent them is, LR1 item is, we can just technically define as A, for example, A drives alpha dot beta comma A. So this is if we have such production rule, after dot operator, if we have beta and the parameter A. So when we are adding or when we are adding the reduce action, so the reduce action after it is just beta is left empty, or if the item is the final item, if the item is final item, we will add the reduce action only under the terminal symbol A, which is appeared as the parameter in the LR1 item. So LR1 item is an item, LR0 item plus the parameter, and parameter is nothing but is the look ahead. So here the way we are applying the closure and go to operation is the same as the way we apply the closure and go to operation in creating LR0 items. But the only difference is when we are applying the closure operation, for example, A drives alpha dot B beta comma A. So this B is non-terminal. This B is non-terminal. That is appeared after dot operator, so we should include the all production rules of B, all production rules of B from the original grammar. But here, when we are adding this production rule, new production rule of B into the item, we should change the parameter. How we can change the parameter is after we consider the internal B, the remaining part will be concatenation. Will be applied the first operation, first of beta and the parameter concatenated together as a single entity. So the comma should be removed from the middle, and just consider beta and the parameter a together, applying the first function. So once we apply the first function on this string, then we find B as a parameter. That is, the terminal symbol appeared at the first position in this string, will be added as parameter when we are adding the production rule of B. That is the only difference that we should consider. And go to operation is added in the same way, or performed in the same way as we added in SLR. And there is no need to worry about the parameters, adding parameters in go to operation. So sometimes we may have a set of items having the same production rule part in LR1 items, like this one, but differ in parameter. So if we have n number of production rules having the same parameter part, the core part, the production rule part, but differ in parameter, then we can unify or just merge together as a single item by taking this single production rule part and separating the parameters by slash. This is the short notation. So let's consider one example on how we can construct the CLR parsing table by considering this grammar. So assume we are given this grammar having those production rules. So S drives A, S drives B, A, B, A drives epsilon, and B drives epsilon. So here, this is a previous grammar. That we have considered in as whether it is SLR grammar or not. So this one is the one we have considered previously, this one. So here let's check whether this grammar is SLR grammar or not, CLR grammar or not. So first we should augment the grammar. Since we augmented the grammar by adding the new internal and then a new production rule. So the how this parameter $sign is added is, as it is the production rule by which we augmented the grammar, we directly added the $sign as the parameter of this item. So then in the same way we just generate items, or applying the closure operation, we can simply add the production rules because of the existence of non-terminal S after dot operator. So we added the production rules of S into the I0. Then the parameter is just the same as $sign here. Why? Because after considering S, there is no any other symbol that can be concatenated with $sign for and calculating a first function on the concatenated string. Since we have only a $sign as a single string with that single $sign, we can find the first of $sign, the $sign itself. That's why we have added $sign as parameter. And the next here, since we have an internal after dot, we should also add this production rule into the I0. So when we are adding, as it is an epsilon production rule, we should simply put dot operator at the right end. Then but here the parameter is different. Why? Because after the consideration of an internal a, the remaining part B and dollar sign. So the together we should calculate the first of dollar sign and this one. First of B A. Obviously the start, I mean the first of this string is A. That's why we added A. And the same similarly for B, we added B, and the parameter is B, because after the consideration of an internal B, the start symbol or the first of this string is B. That's why we added B. Then from this I0 we can generate I1 by applying the closure, I mean go to operator. So go to of I0 comma S. So this is the only production rule that can be added to I1, because this is the only production rule having S after dot. So in the case of go to operator, there is no need to worry about the change of parameter, because there is no change in parameter applying the go to operation. Then I2 can be generated from I0 by applying the go to of I0 comma A. We can apply that like this, and the parameter is the same, but only change in the position of dot. Then I3 can be generated from I0 by comma B, changing only the dot position. The parameter is the same. And I4 is generated from I2, from I2, not from those, because those are final items, and not from I1 because it's also final item, but from I2 we can generate I4. So from I4 we can generate I mean from I2 we can generate I4. And the parameter here, changing the parameter is here the same, but for this item, because of this A, we can add the A production rule from the original grammar. Then the parameter is B, because here B and dollar sign is now concatenated after the consideration of an internal A. So B is the start symbol, I mean the first of this string. And I6 is I5 is derived from I3, and we have the parameter is A, but this one parameter is not changed. And similarly I6 is derived from I4, because from I3 we have already generated I5. There is no need to generate another item from I3. So next one is I4. From I4 we can generate I6, and the dollar sign the same. I7 is generated from I5, the dollar sign the same. I8 is generated from I6, and I9 is generated from I7. And from I8 no need, because this final item. From I9 no. So we have in total 10 items generated from this grammar. So for this CLR parsing table, when we are constructing this CLR parsing table, the structure of CLR parsing table is the same as that of SLR. So that means the action, it will contain the action part and go to part, and the way we fill the action part and the go to part is the same. The only difference is when we are filling the reduce action, we should consider only for the final items, and when as we are just filling the reduce action for final items, we should consider only parameters that is appeared. For example, when we are filling the reduce action for this item in row 8, the reduce action will be added only under dollar sign, but not for all terminal symbols appeared in follow of S, but only under dollar sign. For this one is also the same. And another final item, for example, for this item, the on row 5, the reduce action will be filled only under A, not on under all terminal symbols in follow of B. That's the only difference. So here you can just construct the parsing table for the CLR by constructing 10 rows 10 rows and having those columns. The columns under action are A, B, and $sign, and under go to you'll have 3 columns, S, A, and B. And another example is this one. So you can just consider this grammar, and you can augment, and you can generate the same way we just created. So this is LR1 item collection, and this one is also LR1 item collection. So for this one, as this item is just created, or I mean the set of items are 14, so the parsing table, the CLR parsing table will contain 14 rows, and those 14 rows will be filled. So this is how you can fill the 14 rows. And the columns action table, this is an action part, the action part, and this is the go-to part. So here look, when you are filling the parsing table, the reduce action, the only difference in SLR is the way you fill the action reduce. So reduce action is filled only under the parameters, not in follow. In SLR it was just filled under all terminal symbols under follow of A, but here in this CLR we consider only items, and appeared as the parameter in the final item. So let you check and how you can fill those items, the rows, by the corresponding actions and the state values. So as you can observe from this parsing table, there is no shift reduce conflict, and there is no reduce conflict. So because of this, we can say that the grammar is CLR grammar. The grammar is CLR grammar, or sometimes it is also considered as LR1 items, as it is using LR1 item. So this is CLR grammar. So this one is CLR grammar. So lastly, the type of the LR parsing table is LR parsing table, and this one is the type of LR parsing table that can be just constructed in the same way we construct CLR parsing table. But what is different here in this context is the LLR parsing tables can be constructed by minimizing the number of states in CLR. That is by applying the shrink process. So we merge status. In this case, we merge status having the same core or having the same production rules but differ in parameter. So we merge status having the same core but differ in parameter. And this merging process, or the shrink process, may introduce reduce conflict, not shift reduce conflict. So this reduce conflict can be created in shrink process, but not shift reduce can be created in shrink process. And LLR parsers are just the yak is one example generating or using the LLR parsing table for performing parsing tasks. So here this parsing table may be smaller than the CLR parsing table. The CLR parsing table but may the number of states of SLR and LR parsing table may of a given grammar are equal. So here the merging of, when we are merging, for example, S drives, if we have an item, such item, S drives L dot equal sign R, then comma the parameters dollar sign, R drives L dot, then parameters dollar sign. So another, this is an another item, another I mean the part, this one, the production rule part, we call it the core, the core part. So those are the core part. So to merge items, let's say we have I1 L drives ID, then the parameter is equal sign, I2 L drives ID, the parameter is dollar sign. So in LR1 items, those two different items are considered because they are different because of their parameter difference. So here in constructing the parsing table of LA-LR parsers, we merge items having the same core. So when we are merging them together into one item, we just separate their parameters by slash, taking only one core part, That is how we can construct the LA-LR parsing table. So once we constructed the collection, LR1 collection, we then find out all possible set of items having the same core. For example, we can consider this one, the previous example. So for this example, we just constructed those items, and as you can see, the items I4 and I11 are having the same core. I5 and I12 are having the same core. I7 and I13 is having the same core. I8 and I10 are having the same core. So we just merge them together. 4 and 11 merged together. 7 and 13 are merged together. Their parameters are separated by slash. And I8 and 10 are merged together. So we reduced 4 status from LR1 items collection. We reduced 4 rows. So the parsing table will have a reduced number of rows. So as you can see, from 14 rows, now we have 10 rows. So from those items, I1, and the way we fill the actions and the go-to table is the same. The only difference is identifying the status having the same core and merging them together to be represented by a single row in the LA-LR parsing table. So in general, we do have those 3 parsing tables that can be constructed. And finally, what we can say as another concept regarding the parsing process is, as ambiguity is natural in languages, in formal languages. So we may not totally eliminate ambiguity from a given grammar. So sometimes we may use an ambiguous grammar for just representing concepts. So some parsers may use ambiguous grammars, but obviously their parsing table will have conflicts. But it's possible to use grammars with ambiguity for a different purpose. So in a parsing process, different errors may be detected, but those errors should be the one that can be eliminated or addressed. So the parsers may use different techniques to recover from those syntactic errors. So the errors can be recovered using the panic mode error recovery or using the phrase level error recovery. Okay, now let you work on those questions to measure your understanding on the topics, on the concepts that we have discussed in this chapter in syntax analysis.